Hello, welcome back. This is Economic Statistics, Chapter 7 about sampling distribution. So we are already more than half of the semester. We went past the half of the semester. And from this chapter, what you're going to learn is a little more difficult. It's another level. Because in the first 6 chapters, what we learned are something like in the first 4 chapters, we learned how to define probability, how to define conditional probability, mean, median, variance, standard deviation, blah, blah, blah. And we learned how to calculate them, right? And in the following 2 chapters, in chapter 5 about binomial distribution, chapter 6 about the normal distribution, there what we learned is under several assumptions in a scientific statistical model, how data are generated given parameters, or what are the properties of those distributions. So what we learned so far have nothing to do with inference. We only learned how to define, how to calculate, and what are the properties, how data are generated. So we didn't learn how to estimate, which is actually the ultimate purpose of statistics. That is this chapter 7 is the first chapter to do that. We are going to start inference, right? So basically, statistical inference is to estimate or guess some parameters of interest from data, right? You observe data. From there, you are going to the parameters, going to recover the parameters. And to do that, we need to first understand how parameters generate the data. That was the first 6 chapters. In the first 6 chapters, we learned how parameters are defined. Mean, probability, variance are defined, and what are the properties generated from these data. In the following chapters, we are going the other way. Based on the data, how can we estimate the mean, the variance, the probability, and how accurate they are, or what is the most accurate method to estimate them, right? So then first we learn this way, and we are going to go the other way, and this chapter is a bridge between them. In this chapter, we are going to study the relationship between this and that directions. So, so the title is sampling distribution. So I will explain why it is named as sampling distribution. It will be intuitive. So in textbook chapters, some textbooks may not have sampling distribution chapter, but then in that case, I recommend you to find low large numbers or the central limit theorem. Any statistics textbooks must have those two theorems, low large numbers and the central limit theorem. These two are two fundamental theorems in statistics. Okay, let's go. So first question. You learned the normal distribution. So suppose that X is a randomly chosen person's annual income. And we assume that random variable X, follows a normal distribution with parameter mu and sigma squared. Mean mu, variance sigma squared. So then what is random in this setup? Right? We have random variable X, mean mu, variance sigma squared. What's random here? It is a simple question, right? But can be confusing. The answer is only X. Mu and sigma squared are not random. They should not be random. They cannot be random, right? So basically, when you think of randomness, what is random and what's not, you can think it this way. When you repeat, basically the randomness is defined based on repetitions of random experiments. So if something is random, then different experiments may give different outcomes, different values, right? So in this case, an experiment is to randomly choose a person and ask his or her annual income, right? So if you choose a different person, the income can be different in that sense, depending on who you choose. Your outcome can be different, so the outcome is random. However, when you think about the mean and the variance, so mean is the average income over everyone, across everyone. So by the definition of mean, already you are including everyone into define the mean. So it does not change. So mean of the income is just one thing. It uniquely exists, so it applies to everyone, right? Applies to every experiment, I say, right? Variance is the same. To calculate the variance, the true variance includes everyone's income as an and considers the distribution of everyone's income. So, no matter who you choose, basically you are drawing the random variable from the same variance. So, the distribution from whoever you choose, basically you are choosing one person from the same distribution, and the same distribution has the same mean and variance. So the mean and variance are constant to everyone. Therefore, it is easy to tell. This question is pretty simple, but keep this in mind. It will get confusing. And also, what is obvious is, I said, when you repeat experiment and if you have different values, then the outcome is random. And then what is also obvious is, when something is random, you can define the probability distribution, right? If you repeat the experiment for sufficiently large numbers, then you can make a histogram, and that will be the distribution. And also, you can compute the mean and the variance, right? As long as you can repeat the experiment for a certain number of times, then calculating probability and calculating mean variance is always possible, like for any random variable. So I said this. Then let's think about this. So instead of choosing one person and ask the annual income, I would consider a research center conducting a survey. And what it does is randomly choose 1,000 people, not just one person, and choose 1,000 people and ask their annual incomes, calculate their average, right? Average annual income out of 1,000 people. In that case, is that average annual income out of 1,000 people is random? If yes, think about what is the underlying experiment and why it is random. If you think no, then also think about why you think it's no. So it is obvious, pretty, when you see the answer, it will be easy, but can be confusing. So the answer is yes, right? It is yes. The average of 1,000 people is random because if you choose a different set of 1,000 people, the average can be different, right? If you happen to meet rich people, then your average will be high, just happen to be high. But if you happen to meet like poor people by chance, then your average will be lower. So your average, the average you calculate, it depends on who you choose, which happens by chance. So it is random. Okay, and then so then we can understand choosing 1,000 people as one experiment, right? So repetition of that experiment is choosing another set of 1,000 people, right? So, or you can imagine like that. So if you repeat this experiment 10 times, an easier way to think about is, say there are 10 independent research centers, and they independently choose 1,000 people and calculate their average income. That is exactly 10 times repetitions of this survey. Of course, different research centers may get different results, different averages, because they are random, they are independent. So literally, the X bar is random. The main reason why you may think it is not random is because X bar is the average. Average is the mean, and mean is this mean. This is also mean, and I said the mean is not random. Here the mean is not random, but here this average is random. Why are they different? Simply speaking, it is true that it is also a mean, a kind of mean, but just their names are the same, happen to be the same, but to be more exact, we should have said this mean is population mean. This mean includes everyone, literally everyone you can imagine. However, this mean includes only those who you observe, right? If you choose 1,000 people, to calculate this mean, you only include 1,000 people in the calculation of this X bar. So also what underlies this X bar is population mean. So this is calculated from 1,000 people, but at the same time you can imagine mu is the true mean that is calculated from infinite number of people, right? So you cannot observe that, but mathematically you can imagine that. Theoretically, there exists a true mean, and your sample mean is a kind of an estimator for the mean, for the true mean, using only 1,000 people instead of everyone, like every adult in the world, for example. Okay, so we need to distinguish the sample from the population, right? The population is a kind of infinity world. Like it's infinity, like you cannot observe everyone. If you could observe everyone, then there is no inference. It's just a matter of computation, right? If you observe everyone's like income, like for example, if you have text data, then why do you need to do survey? Or you don't need to do any estimation. You are just calculating their incomes. That is the true income. But statistics is needed because we cannot observe everyone's income. Instead, we observe random sample, which is just a part of everything, which is just a part of everything which are observed. And we are going to denote a random sample this way. We observe n number of observations. So as before in chapter 1, we define this n. Usually n denotes the sample size, right? So you observe, in our example, we observe 1,000 people's income. So that is a random sample. We have 1,000 numbers, and we can denote them as x1, x2, up to x1000. That is random sample. And also, not just observing a lot of numbers makes a random sample. You need two assumptions. First, identical distribution. So all these 1,000 people must have the same distribution, right? So we are going to, this is obvious, right? So if you think about the mean calculated based on everyone, then automatically it has the same mean. Similarly, same variance, same distribution is considered, right? Identical distribution. So everyone has the same distribution. And the maybe more important assumption is assumption 2, independence. All observations should be independent with each other, right? For example, like suppose that if you happen to, like, suppose if you survey non-randomly, for example, if you survey on campus, for example, then you are surveying only college students or professors on campus. So it is not independent. They are related because they are similar. If you do survey in this area, then you are going to observe similar people, so they are not independent. Really, to be independent, you need to really randomize the choice of people. It is not easy. So in statistics, there is an important field like, say, survey design. You have to correctly and carefully design a survey to make sure the observations are independent with each other. So, like, the first person's observation, the first person's outcome has nothing to do with the second person, right? So, it is a very important and theoretically important assumption. Okay, so throughout this course, we are going to maintain these two assumptions. Whenever I say you have a random sample or you have data, you have like observations, I will maintain these two assumptions, which is natural. So what we learned so far is, as I explained earlier, you have parameters, and if you random sample from the population, then you are going to observe some distribution, right? So, like we learned, as if we could repeat the experiment as many times as we want. But from now on, that is not possible. We have to admit that we have limited observations, right? That is the main problem. So, we only considered one experiment generates one observation, and we repeat. But now, one experiment is random sampling, which means one experiment generates a set of n observations, not just single outcome, right? And from the random sample, we are going to calculate one number, x bar. So, in the previous chapters, I said one experiment generates one outcome. But now, what do you have in mind is one experiment generates, observes many observations, but in the end, we are going to generate only one number, which is the average of the observations, x bar. So, basically, the structure is the same. One experiment generates one number, but one number now, what we have in mind is x bar that is calculated from 1,000 observations. So, it does not cause any difference. And then another confusing thing is, when I say repeat, so already you may think experiment is repeated 1,000 times, but actually not. What I have in mind, as I said, one repetition is generating 1,000 observations and calculate one average. So having one average is one experiment. Okay, so you have to imagine different research centers, not just choosing another person. The unit of observation is 1,000, right? So, and from there, if you can repeat this experiment, found another research center and do the survey again, and then you are going to get many repetitions, and then you are going to get some distribution of the average, right? Distribution of average incomes from different research centers. So we can think of a distribution based on that because it is random. So this is an important thing, important concept. So hypothetical repetition of random sampling experiments are like this. So you imagine 1,000, 100 research centers, and each research center surveys 1,000 people, and they report their average income. So we observe, in this case, what we observe is not 100,000, but we observe 100 averages, right? One research center is one experiment. And if you build more research centers, and if you could have infinite number of research centers, you can think of sampling distribution, distribution of their averages. So we are going to call that sampling distribution because one experiment is random sampling. And then we can ask the same questions as before, like what is the mean and variance, and what is the probability distribution. Interestingly, we can answer all these questions with ease. Pretty simple. Of course, mathematically complicated, but the results are pretty simple, so the answers are simple, right? So let me confuse you. Let me challenge you. So I said, like so far, the main thing is we need to extend our idea of experiment, and then automatically we can extend the understanding of randomness. So don't be confused by the name mean. Say, I said x bar is an average, but average is mean. To be more exact, we should have said it as a sample mean because it is calculated only from the sample. So I said it is random. That is okay. So when it is random, you can think about its expectation. So I'm going to think about this, which is mean. Expectation is mean of a sample mean. So this causes the confusion. What is mean of a sample mean? This is a mean, this is a mean. But to be more exact, this should be population mean. So this mean, the first mean is expectation is theoretical, is based on theoretical, like hypothetical repetitions of the random sampling. And the second mean is based on your observations. So the way you calculate these two means are different. This is theoretical population mean. This is more practical, empirical, and finite sample mean. So to reduce the confusion, I will try to call x bar as average or sample mean, and expectation, the population mean, the theoretical true mean as expectation, right? So this is the biggest problem in understanding sampling distribution. What is random, what is not? Yep. Okay, in the next video, I'm going to think about even easier example. Dice, rolling a dice. Suppose that you are throwing 2 dice. This is a kind of random sampling. In the simplest possible case, you in one experiment is throwing 2 dice at the same time, and you are going to calculate the average of these 2 dice, right? And then in this case, this is simple distribution. Now, calculate probability that the average equals 6. Okay, I will stop the video here. So I'll try to calculate this and continue to the next one. Okay, see you later.